Okay, this is our first topic review video, and I'm sorry it took so long to do it. I have not been feeling well, but also it's a little overwhelming, you guys. I could see why it's so difficult for you guys to sit down and study. When I consider this, I do consider it by topic, and so I would recommend that the place you start from is to choose a topic that's going to get you a big chunk of points. And then my next question was, which year do we start with, or which regions do we start with? And that's partially because first, I'm always trying to guess which one they're going to use questions from. But then also in my class, we've done so many questions from June 2024. I feel like you guys have just sort of memorized them, and I'm not sure it's worth it for us to go over them again. So I may slide down here to August of 2024. And I think the topic I want to look at first is actually going to be equilibrium and kinetics, or energy and kinetics. And that's because it's a topic we don't do a lot of. It can sometimes be a lot of questions on a Regents, probably between 8 and 10 questions. That's a lot of points. And if you've already got a lot of aqueous reaction stuff down and you're pretty good with some of the other questions, this might be a topic you want to add to try and pick up more points, and you might need some help with. So at the top of my menu bar, if you can see it, I've got all my stuff opened and ready to go. I've got our New York State Regents exams. I've got the core curriculum because I want to show you what the core curriculum says. And then I've got my reference tables ready to go in case I need them. And then I've also got pulled up our notes from equilibrium and kinetics. So I'll link these slideshows in the description for people who want to go over them again. These are from quarter 2, and this was the fourth topic. All right, so let's go straight into the questions. According to my topic guideline, the first question for energy and kinetics on the August 2024. Now, August 2024 was a great Regents to start with because they didn't give you any part twos on equilibrium and kinetics. And to be honest, the easiest way to get points is to have multiple choice questions about the topic, because that will give you kind of a limited framework for what kinds of stuff you have to recognize. Whereas a part two question might ask you to do something like sketch a potential energy diagram. Um, and so we probably don't want to get into that necessarily. But everything that you learn from that section can be used on a part two section also. And that's why I want to go over the core curriculum. So remember that when they're writing the test, they're making sure they include a number of these points that are written as a list for you on the core curriculum. So I went over this in the first video. This is basically a great place to come for your master study guide. It doesn't mean you're going to understand everything on this list, and it doesn't mean that everything on the list is going to be this straightforward, but like they might be describing a concept you have to do math work for, but actually not for collision and equilibrium and kinetics. These are mostly either concept questions or using table I, which shows you if a reaction's endothermic or exothermic, uh, writing a thermochemical equation, which is an equation which shows energy as a reactant or a product going in or out of the reaction, and then just potential energy diagrams, which is a diagram of the energy changes as a reaction is proceeding. So let's go through this list really quick because I want to make sure you know what we might be looking for. There is a theory called collision theory. This is it is what it looks like. A collision is when two things crash into each other. They're basically saying there is a theory, a model for how we discuss chemical reactions, which involves the two particles of reactant crashing into each other. That's how we talk about it. And they only can successfully react if they have enough energy when they hit each other and they're facing the right direction. And this is because some molecules, so orientation means your position in space. So these are three-dimensional molecules. And if you're not facing the right way, the part of your molecule that is most reactive might not be hitting the other reactant molecule. So you have to be actually facing the right way. This comes much more into play if you're a really big molecule. like a big, awkward organic molecule. Okay, the rate of a chemical reaction, that's the speed at which a chemical reaction will happen, depends on several factors. Now, we have done many of these factors in the lab. So the first one would be temperature. Think about the way we did this with a physical change like solubility. Solubility was increased by increasing the temperature of the water because it gave everybody more of that kinetic energy to hit each other more effectively or to get interact with the water molecules more effectively. Now, please keep these things separate because when you dissolve something, that's a physical change. If I take people who are doing a reaction, though, and I heat them up, I will speed up the chemical reaction also, because just like it says up here, collision theory says that if they hit each other with more energy, there's a better chance you'll get an effective collision and the reaction will happen. So this is like when I say to you in the lab, don't wash your hands with hot water. If you get chemicals on your hands, rinse them off with cold water only. That's why. Because if you have something on your hand that is reacting with your skin, you don't want to speed that reaction up. You want to slow it down. Okay, concentration has to do with how much of each ingredient you put in. A lot of times, if your solution is very strong, so you saw this in the lab again, think back. We did a bunch of reactions using copper sulfate. Okay, the first time we did copper sulfate and aluminum foil, we used a weaker solution, but pretty strong still, of copper sulfate, just to see if we could look at the different way that change the rate of the reaction. Okay, the second time we did it when you actually made copper to keep, I used a very strong solution of copper sulfate. And so you saw that reaction was very violent. It was much more bubbling, much more smoking, and then it got really hot. It was way more exothermic because you had a high concentration of reactants. The nature of the reactants, some things are just not that very reactant, like the noble gases. Some things are sort of moderately reactive, like copper and aluminum are reactive, but not necessarily like you just leave them on a table, they'll just look at you. But they will sit and slowly react maybe with oxygen. Aluminum's actually more reactive, but it has this little defense mechanism where it covers itself in aluminum oxide and then it's not as prone to reacting with oxygen in the air. Um, the one we did in the lab where you changed the way you put the aluminum foil in, okay, that was about surface area and also about catalysts. Okay, so if you lower the surface area, you'll slow the reaction down. That's what happened when you rolled your aluminum up into a ball. That was low surface area. High surface area is when you rip stuff up into little pieces. So in questions, you're going to see things like this one is a big chunk of metal and this one is a powder. Which one is going to react faster? The powder, because when you grind it up into little pieces, you increase the surface area a lot. Okay, so hopefully you have some recollections of these things. And the presence of a catalyst doesn't always necessarily speed a reaction up that much. What it does is it makes the reactant and the product more likely to interact with each other. This lowers the amount of energy it will take to get them to get together. And that's called your activation energy. So if it lowers the activation energy, it gives everybody a chance to meet and react with each other in a different way that takes less energy and is less awkward. So it's kind of like, you know, helping your friends to play a game to get to know each other at a party. So what it doesn't do is it doesn't change the energy that the reactants come in with or the energy that the products leave with. It just changes how they get together to react and lowers how much energy it takes to get them to do that. So we'll look at that on a graph also. But you can also just consider that the presence of a catalyst on the Regents, they do not just want you to say it speeds up the reaction. I'm going to say this over and over again. One of the years, they said on the answer key, If you say it speeds up a reaction, we will not take the answer. You have to say it offers an alternate pathway for the reaction and it lowers the activation energy. So those are the two key phrases. Okay. And then we'll talk about chemical equilibria. Le Chatelier's principle is when you mess with a system that's already at equilibrium and see how it responds. Energy, this is that definition that came up on the multiple choice questions on the final. This is the definition of change of enthalpy, also known as heat of reaction, and that's the little triangle H that's in table I. How you get a number for each one of those reactions is you subtract the amount of energy that the reactants had from the amount of energy that the products came out with, and you get a number. That number, if it's positive, means that that reaction was endothermic and it absorbed energy. And if it's negative, that means it was exothermic, it gave off excess energy. Um, so here it is. A catalyst provides an alternate reaction pathway, which has a lower activation energy. That's what they're going to be looking for. They're not going to be looking for you to just say it speeds up the reaction. That's like a seventh grade life science answer. Okay. We need you to move up to the more sophisticated answer now. Don't fall back on your prior knowledge for this. Entropy is not the measure of randomness or disorder in a system. It is a good beginner definition. It's a little more complicated than that, but generally they're going to give you questions where you are creating a less ordered system. We've actually done this a lot. If you are looking at a sodium chloride crystal, remember that picture I've shown you hundreds of times of little silver atoms lined up with little green atoms in a perfect rows to make a cubic uh, crystal structure. That's what sodium chloride looks like. It's very orderly. Everybody has a place. It's not, everybody's not all over the place. That orderliness represents a very low entropy in a system. So crystalline structures of any kind where people are, when you say crystal, what you mean is everybody's lined up in a perfect rows and together they're making a pretty shape. Crystals just make pretty shapes, right? They make cubes, they make quartz crystal shapes. If you look in the slideshows, there's pictures of crystals everywhere. Crystalline solids represent the lowest amount of entropy, almost zero in most cases. So anytime you're going towards a solid from a gas or a liquid, you're reducing entropy because everybody's lining up and becoming more orderly. If you're going from a solid to a gas, you're becoming less orderly, so your entropy is increasing. And basically, a lot of systems in nature tend to go towards lower energy, like they're losing energy as things are happening to them, and that's increasing their disorder. All right, let's get into the questions because I don't want to make this video too long. I'm going to go back and index this so you could see which stuff you need to go over. So for this one, we only have to do multiple choice questions. I will tell you when you're looking at the test, there is a little bit of an order. It bounces back and forth, right? In the beginning, they usually start off with maybe 3 or 4 questions that have something to do with atomic structure. Then they'll start to get into whether or not you know kind of your basic chemistry. So a lot of your physical change and basic ideas about chemical reactions or systems starts to show up over here. So do you know the definition of a compound? Oh, hold on, you guys. Sorry. When I changed sharing windows, it decided it didn't want to show me. All right, sorry about that. I'm talking about Regents you can't see. Okay, so this is August 2024. You'll see the first 3 questions on the left. are about atoms and atomic structure. This is definition of an isotope and some things about particles and energy levels in an atom. Then it goes straight into kind of this mixed bag of topics from the middle of the year. For like, do you know what an allotrope is? That is in chemical bonding in my slideshows. Do you know the definition of a compound? Do you know the laws of conservation? There are three things that are conserved in every chemical reaction: mass, charge, and energy, right? And I'm looking at this list and none of those things are on here except charge. Density, molecules, and temperature are not necessarily conserved. Oh, that's a tricky one. All right. We'll talk about that in a different video. Um, Metallic bonding, ions, and gaining and losing electrons. Do you know what makes something an ion? This is actually a great place to start, number 9, because this is technically an energy and kinetics question. And there is a cute little acronym for this, number 9. It's not really cute. It's kind of weird, actually. Um, I came across a student who had a tutor give them the wrong information here. There is an acronym for this I learned from a chem teacher at my old school, BARF. And it says breaks absorbs. That's what that stands for. Breaks absorbs, releases, forms. And what they're talking about is a bond. When a bond breaks, it absorbs energy. When a bond releases energy, it's because it's being formed. So here's how I explain it to you guys. And I can see from your part 2 answers that my little stories stick sometimes. Essentially, people make bonds because either they need 8 electrons in their outermost shell, and also energetically, they have too much energy. They would like to get rid of that excess energy. Going down to that lower energy state, giving that energy off, and reducing your entropy is often energetically favorable. Now, it doesn't mean that you didn't make more entropy when you did that, when you lowered your energy level. It just means you don't have the disorder. The disorder sort of goes out into the world and makes more entropy around you. Different conversation. Okay, so here I have 2 fluorine atoms. Remember to read this as a sentence. It's not a math equation. Please stop writing equal signs on your chemical equations. This is if I take fluorine and another fluorine, and this arrow represents a process. And during this process, they make a bond and they become a F2 molecule. They are now together, chemically bonded to each other, sharing electrons. What does this do for them? Okay. It lowers their energy level and makes them more comfortable. If you have reviewed the slideshow on the beginning of the periodic table, you will know that elements in group 1 are the most reactive metals, meaning that they do not like to be unbonded. They will bond with almost anything. And fluorine and everybody in group 17, these are your most reactive non-metals. So the alkali metals, group 1, and the halogens, group 17, are very important. They get really confusing for you guys, though, because literally the most reactive non-metals, many of which are gases at room temperature, are right next to the least reactive elements on the periodic table, the noble gases. And so that's really confusing. If you haven't sat with your periodic table and known the difference, it's kind of weird, right? Like you've got 2 countries who are total opposites of each other and they're right next to each other. Um, so if you've just got kind of a general sense that there's a bunch of gases on the right-hand side of the table and they may or may not be metals, you don't know your periodic table well enough. And that's going to cause problems for you. So when fluorine, this very energetic atom, makes this bond, he does it so he can relax, right? He does it so he can get rid of that excess energy and be comfortable, be more stable. So that extra energy, where does it go? They give it off. So this would most likely be, I don't want to say it's an exothermic reaction because um, It's not always an exothermic reaction, but essentially the overall energy change will be that its energy will be released. This is pretty typical for when you're making covalent bonds between nonmetal. So you'll see this question a lot. Sometimes you'll see the opposite one. They'll take the F2 and they'll break it into two fluorines. They were comfortable when they were bonded, so that would require an input of energy. So the answer to this one is a bond is formed and energy is released. So that's the second part of BARF, released, formed. The first part would be if they gave you the opposite question, um, broken, absorbed. I didn't want to accidentally say B was bonded because that's going to give you the wrong answer. All right, let's see. Off of our topic sheet, who else are we looking for? We are looking for 16, 20, and 21. Which term represents a form of energy? This is memorization. I'll tell you right now, for chemistry, there are many types of energy. For chemistry, we learned thermal, mechanical, chemical, nuclear, and electrical. Okay. Chemical energy comes from a chemical reaction. Electrical energy is any kind of energy that produces an electrical flow of charged particles. So it could be a chemical reaction like a voltaic cell producing a flow of electrons, which is now electrical energy. So that really kind of comes up when we do batteries, but we use electrical energy to excite atoms when we put a sample of gas into an electrical power source, whereas we use thermal energy when we stick an element in the fire and look at the color change of its electrons getting excited that way. Okay, thermal energy technically is simply based on the movement of particles. If you uh, mechanically make particles move, you will generate heat. That is thermal energy. So, for example, if you rub your hands together really hard and make a lot of friction, that's a mechanical energy. And that energy is actually going to produce some heat. If you shake something a lot, you actually are introducing thermal energy. Thermal energy has to do with the movement of particles in a substance. The more you get them to move, the more thermal energy they have. All right. So these other things are not even energy. Molarity is the concentration of a solution, how strong it is. Volume is how much space it takes up. And temperature is a measure of the average kinetic energy in a substance. Temperature is a measurement. It is not a form of energy. So this is the number one thing people will screw up. Temperature measures how much thermal energy is in a substance, how much the particles are moving because of however they're moving. That kinetic energy the particles have. If you have a substance that is very cold temperature wise, what you're basically saying is that the particles are not moving very much. And that's a reduction of their kinetic energy. So temperature just measures it. It is not the energy itself. Thermal energy is the energy you're measuring, essentially. Okay, but I know you guys know that these two words are related, and so you're likely to mess them up. All right, 20. A reaction between two different gases is most likely to occur. Okay, so this is basic collision theory, and this is somewhat memorization. According to collision theory, molecules will react if they hit each other with enough energy and they are facing the right direction, they have good orientation. Okay, and they basically hand it to you. They say proper orientation and sufficient means enough, sufficient energy. The other three things don't really have much to do here. I could see you accidentally messing up charge because I think sometimes that concept doesn't feel like something you 100% understand. But I could tell you that it's not mass and volume. Mass is just how much matter there is in something, and volume is how much space it's taking up. These are physical properties. They have nothing to do with how something's going to react. Your chemical properties are based on your what your electrons are doing, like something about your actual atomic structure. They have very little to do with how much of you I have and how much space you're taking up. Now, this gets a little bit confusing because mass and concentration are not the same thing. When I say how much of you I have, I'm not really giving you any information about how available you are to react right now. If I'm talking about concentration, I'm implying I put you in water. If I dissolved you in water, you're way more available to do a chemical reaction. So mass is an important physical measurement, but it doesn't give us a whole lot of information about the about the things that are happening in the situation that might make a reaction more likely. Like in terms of doing lab work, if I just gave you the masses of all my ingredients, it wouldn't give you very much information about how I was going to get that reaction to happen. Like what forms are my ingredients in? Am I heating things up? Am I adding a catalyst? How am I mixing these things? That kind of stuff that you actually need to know about whether or not something's going to react. So charge also doesn't have a whole lot to do with whether or not things are going to react. Charges are more related, they are related to bonding. This, I could see why you guys get confused about this. Um, here's what I'm going to say to make this clearer. Collision theory is what we call a model, meaning it's a set of ideas that explain how reactions happen in one way. That model is all about collision. It's all about whether or not two people are going to hit each other. And in this case, we're not really factoring charge in. It can be a factor, so I could get why you could overthink this. But for the collision theory model, mostly looks at whether or not people have enough energy to hit each other and whether or not the reactive side of their molecule is going to hit the other person. So let's think of it that way. We're just going to limit it to what the model talks about. All right, now 21 talks about a much more sophisticated concept, which is chemical equilibria. A chemical equilibrium is a very complicated thing to explain. It's usually a concept people really have trouble with. I have a whole slideshow on this. So I'm going to link all of these slideshows. I talk a lot about what an equilibrium is here. I go back to our earlier conversation about physical equilibria, and then I try and work us up to chemical equilibria. So this is physical equilibria. Physical means you have no chemical reaction happening. This is just water in a flask with a cork in it, and it has three physical states it can be in. It can be a solid, it could be a liquid, it could be a gas. If you have a liquid and it starts to evaporate into a gas, you can have a physical equilibrium between its gas and its liquid forms. So these are what are known as physical equilibria. But the term equilibrium in chemistry, really in everything, but it it's a deceptive term. Okay. Equal in the beginning of equilibrium does not refer to quantities, right? So I don't have equal amounts of water here and water vapor. What it refers to is the rate, the speed at which the process is happening. Okay, so you have two opposite processes in every equilibrium. Something that's happening in one direction, and then literally something that's undoing what you are doing, right? So let's talk about that in a physical equilibrium first. Let me just zoom in on this. The two processes happening in this flask, I've got a liquid, it's vaporizing or evaporating into a gas. That's process one. I've got a gas, look at the arrows going in the other direction, going back to being a liquid. That's condensation, the opposite of vaporization. That's the opposite physical change. So those are my two processes. I have two processes happening at once. I'm evaporating molecules I'm condensing them back into liquids. So I've got some going to a gas, some going back to a liquid. If that's happening at the exact same speed, for every water molecule that becomes a gas, one becomes a liquid. Essentially, I'm going to reach a point where nothing's going to change, right? So if every time you go to the store and recycle a bunch of cans and bottles, you go back into the store and you buy the exact same amount of soda, you will walk out with the same amount of cans and bottles you came in with. So if you keep recycling them and drinking soda at the same speed, you're always going to have cans and bottles to recycle. Do you see what I mean? So the example I usually give for what equilibrium really is it's a constant movement that's getting it to look like things are staying still. So this is like I always say it's walking up the down escalator. If you run up the down escalator and then you walk in the middle of it at the same speed that the steps on the escalator are moving, what you will get is it will look like you're just not moving. You're just standing in the middle of the escalator. It's important to note that you are moving. That's exhausting, right? Constantly having to move at the same rate of the escalator just so you can stay in the same spot. So equilibrium does not imply processes have stopped. It just implies that whatever you're doing, because you're doing one thing in one direction at the exact same speed as you're undoing it, the overall, from the outside, it appears that nothing is changing, but that's not true. But what is true is that you are getting everything to stay constant. You're getting you're getting it to stay that you always have the same amount of soda in your house and the same amount of recycling to bring in because you're always at equal speed. You're drinking it as fast as you're recycling it. So the equilibrium refers to that the two processes are happening at the same rate. From the outside, it will appear that nothing is changing, but actually everybody's working really hard to maintain that appearance of quietness. This is oh geez, there, you know what? There's a funny saying that kind of goes with this about ducks, right? People who are in tough situations who work really hard, other people will say to them, geez, you look so calm though. And they're like, oh yeah, no, but I'm like a duck. I look like I'm serenely floating on the water, but underneath I'm paddling like crazy to keep myself up, right? So that's kind of what this is about. Um, you will, the hard work you're doing, it will make it so that these don't change. The amount of gas and liquid you have don't change, but the amounts are irrelevant. They're not equal to each other. Okay, so the equilibrium is about rate. That's the very important part. Okay, so then it's going to get into chemical equilibria and solution equilibria. So this is what a chemical equilibria looks like. And now you know about acids and bases. So this is a symbol that represents an acid. It is the A is not a real element. It's just saying whatever this is making this hydrogen an acid. Weak acids and bases go into chemical equilibria in Bronsted-Lowry reactions. And that's why they all have double arrows. Um, and so you've actually seen this recently when we did acids and bases. So the rest of this slideshow goes over chemical equilibria, a very famous examples of chemical equilibria. And the reason why I bring up the famous ones is because they're going to use the famous ones on the Regents. I'm not just bringing them up like for historical fun facts. So the first one you should be aware of is that weak acids and bases, those are ones that follow the Bronsted-Lowry theory. They're proton donors and proton acceptors. That was acid and base in that order. Um, the other ones are, this is a famous example, N2O. If you cool it down, you will get dinitrogen tetraoxide. And if you heat it up, you will get nitrogen dioxide. This is sealed in a container. It can't get out. And so this is actually happening in the container, a reaction where they shift to the other reactant or product based off of the temperature. And the other one would be the famous Haber reaction, which is a reaction I use a lot to talk about balancing and et cetera, et cetera. It's famous because Fritz Haber won a Nobel Prize for it, except Fritz Haber was evil, an awful person. He didn't start out that way. I guess that's the story a lot of people tell. Um, but this is a famous equilibrium reaction where he actually, that's what he won the Nobel Prize for, was manipulating. They already knew how to do the reaction. He manipulated the pressure and temperature um, to get the reaction to produce more ammonia. And what he was doing was manipulating an equilibrium to get it to shift in a direction he wanted it to without ruining the reaction. This produced ammonia for fertilizer, which kept a lot of people fed. And so those are reactions you're probably going to see. All right, let's head over to question 22, 40, 41, and 50. All right, so 22, again, this is a catalyst question. I already went over catalysts. Catalysts increase reactions by providing, they tell you in the question that it provides an alternate reaction pathway. So if this were to come up in a part two question, and they did goof and they put it also in the part one, make sure you come back here and steal this, because this is the answer to what enzymes do. This is what catalysts do. So they offer an alternate reaction pathway. Now think about this for a second. They don't participate in the reaction itself. In other words, they're not part of the reactants and they're not part of the products. Therefore, they cannot raise the heat of the reaction or lower the heat of the reaction. The heat of the reaction, or the amount of energy that the reactants and products come in with and leave with, that's their own thing. That's part of their own chemical makeup. And so that's not going to change. All you want to do is to think about this like a party, right? If you're trying to get two of your friends together so that they meet each other and date, you want to be the catalyst in this situation, right? You can't change who they are as people. You're just going to try and get the situation to work out to make it easier for them to get to know each other. And then maybe the next thing you know, they're sliding into each other's DMs. My slang is terrible. That was probably like a bad dad joke. Sorry, you guys. Right? So it has nothing to do with their heat. They're also reactants and products. Well, heat of reaction has to do with the difference between the reactants and products. And since we're not changing their energy level, we're going to knock these answers out. We're not changing who they are. All we're doing is making it easier for them to meet, right? So if the activation energy is how much energy it's going to take for you to get them to sit down, talk to each other, if that's really high, if that's really difficult, they are not going to, if you're going to have a hard time. Like that might be one of those situations where you're like, oh God, please don't bring your best friend and then talk to them all night and not talk to anybody else, because now my friend Brad is never going to be able to talk to you, right? So the catalyst part is getting your friends into a position where they're going to actually talk to each other for long enough where maybe it turns out they have some things in common. So you don't want a high activation energy. You don't want to make this situation difficult. What you want is a low activation energy. You want to provide a pathway to make it easier for them to start to talk to each other. Right. I hate using the dating metaphors because I think they're a little loaded, but um, it's a good metaphor if you're trying to think about what's going to happen. All right, let's go over to 40. I'm not even going to show you what that looks like on a graph, you guys. I'm going to link the slideshows. The graph's on the slideshow. The graph is easier to read if you already know what I'm talking about. Activation energy is usually labeled, but if they turn around and give you like a big long part two on a reaction coordinate with potential energy diagram, you're going to need to study that. So I'm going to show you which slideshow has that. All right, 40. is it looks complicated. Okay, this is in my slideshow on multiple choice questions. This would be an example of a big old multiple choice question that's too freaking long. And then there's an equation, so now you're annoyed because you don't like reading equations. Um, so it's a two, each one of these is a two-part answer and it's really long. So first off, before I even start reading the question, I'm going to say that I'm going to remind you that one of the things you want to do when you have these long ass answers is you want to cut each answer in half. So if you read this first answer, it says the equilibrium shifts to the left and the concentration of SO3 decreases. At each of these ends, you want to cut this sentence in half. Okay, so when I first tackle this, after I go look at the question and try and figure out what should I be looking for, I am going to not try and do the whole answer. I'm going to try and eliminate at least two of them based on the first half of the answer. So according to the first half of the answer, this reaction is either going to shift to the left. So both of these say left. Or it's going to shift to the right. Both of these say right. So two of these are going, either 1 and 2 or 3 and 4. I don't know which ones yet. But before I even worry about what's going on with the concentration of the SO3, is it decreasing or increasing? You know what else I don't like that they do in these questions? Notice that these are the same, right? Shifts to the left, shifts to the left. Great. These are all together. It makes it easy for me to figure out whether I'm knocking them out. But then on the second part of the answer, they alternate them, decrease, increase, decrease, increase. This makes it even harder for you to not accidentally just pick the wrong one, even if you know what you're supposed to pick. So we have to be real careful. Get your ruler out, get your highlighter out, get a blank piece of paper and start covering stuff up so you can't mess this up. This also for me, if this was not my best topic, I would circle this and come back to it because it's long and you're going to need to sift through it. So come back for it after you do easier questions, which actually 41 is an easier question. So they're saying that this is a chemical reaction at equilibrium, and here's my double arrow, which says that this is at equilibrium. Another important thing I have to look out here is that this reaction has energy written on the product side. Okay, so this is my side where it tells me what happened, what I made, and this is my reactant side, tells me what my ingredients are. So when sulfur dioxide reacts with oxygen, remember I'm reading this as a sentence, not a math equation. This represents and or combines with. It's not really quite the same as adds because when you're doing math and you sum two things together, you know what you're going to get, right? 2 plus 2 is 4. If you're doing a chemical reaction, you don't always know exactly what you're going to get because you don't have to get one product. You might get 2 or 3 different products, right? So you may not just make everything together. This is why I'm not allowed to read this as a plus, okay? So I have a process here that is happening, but what the double arrow is implying is that this process is reversible. And that means I don't just have one process happening. I have 2 processes happening here. Okay, I have what's known as a forward reaction, which goes to the right from left to right. This is my left. This is my right. I'm going to write that because you're allowed to talk about it that way if it's a part 2 question. Okay, I have going forward sodium, geez, oh man, that's like a terrible mistake I would yell at you for. Sulfur dioxide reacting with oxygen and going forward, it's producing sulfur trioxide. Okay, and when it does that, it's giving off excess energy. But if I'm reading the reverse reaction, what this reverse reaction, the bottom arrow is saying, is that if I put energy into the reaction, I can get sulfur trioxide to break up into sulfur dioxide and oxygen. Okay, so going forward, this is a synthesis reaction. Going backwards, this is a decomposition reaction. I've got this process happening at the exact same time. If the system is at equilibrium, what's happening is This is like going up the down escalator. These guys are furiously reacting, but they're just sort of looks like they're not getting anywhere because every time they do one thing, they undo it. Okay. So if I increase my temperature, if I increase my temperature, what I have to think about is what's happening to these guys. Which one of these things is going to be affected? What's going to be affected is it's like I added more of this. According to Le Chatelier's principle, Le Chatelier is a French guy. Uh, if you stress an equilibrium, the first thing it will do is try to absorb the change. And it will try to make that part of the reaction go back to exactly what it was doing before. The rest of the reaction sort of will pay the price for whatever needed to be done in order to get that to happen. Okay. So if I increase energy, what the reaction will do is try to absorb the extra energy and use it up and then get back to what it was doing and be back at an equilibrium again. So if I were to increase my product, now I have to use up what's over here, get rid of it so I can go back to being at equilibrium. The only way to use this energy is to do the reverse reaction because that uses energy, the reverse reaction. So the reverse reaction uses energy to break up SO3. What will happen is this will decrease, the whole reaction will shift to the left, and I will make uh, more of my product. And I'm saying product even though I'm on the reactant side because I'm following this arrow on the bottom right now. So I'm doing what's known as the reverse reaction. I'm going backwards. Okay. So first things first, I know that this reaction is going to shift to the left. This gets rid of these two choices. Now I have a 50-50 shot of getting it. The second part of this, now I get to look at the second part. The second part says that my SO3 is going to decrease or increase. Now, if I'm going backwards, I'm making this stuff. So I'm going to make more of it. So it's going to increase. Okay, I know that that's nowhere near as easy as you would like it to be. Um, but it's still doable. So it's a very doable question. If you were to do this at the end of a Regents and try to work it out, you'd probably be able to figure it out. All right, we are almost done. Sorry, you guys, I know these take a long time, but I am going to index the video so you could do different questions. Which phase change results in an increase in disorder? This actually is an easy question because we just went over entropy and disorder, right? You want a phase change that goes from uh, a more ordered state to a less ordered state. We want an increase in disorder. So just be careful that you don't misread the question. So you can make a little note for yourself. That'd be great. Imagine that, right? If you're thinking, let me start with gas because it's the least orderly state, right? So gas to liquid to solid. Which one of these is the most orderly state, right? This is much more orderly. So as I'm going this way, I'm increasing disorder. So I just want to check each one of these answers against that. And I'm going strictly by the subscripts. Subscripts that say gas, solid, liquid gas, blah, 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 right? Is moving from a gas to a solid increasing my disorder? No, get rid of it. Is going from a liquid to a gas increasing my disorder? I should draw this arrow a different way. Okay, high entropy, low entropy. Let's say it this way. So if I'm thinking about increasing disorder, I want to kind of draw my diagram to help me. So this way is increasing disorder, right? So if I'm going from a liquid to a gas, yes, I'm increasing my disorder. So check that one. Do I want to check the other ones? Let's just be careful, right? Gas to liquid, no, I'm decreasing my disorder. Liquid to solid, oh, absolutely not. That's it. It's that one. And I don't even care what it is. I don't care if it's chlorine. I don't care if it's water, whatever. All right, so it's 2. That was a pretty easy one if you know about disorder. And they didn't even use the word entropy. So it was like you didn't even have to know the vocabulary, you just had to know. And you guys know that. All right, there's only one more left. Let's just knock it out before we end this video. That was number 50, 45, 49. Oh, another equilibrium. Woo, that's a lot of equilibriums for one test. Okay, given the equation representing an equilibrium, and this is an acid in equilibrium. Oh, except that it's an acid-base question, but it brings up equilibrium, so I put it with the kinetic in equilibrium. All right, but this is actually an acid-base definition. So remember I said, you guys, Bronsted-Lowry acids and bases involve equilibrium. This is an acid. And the reason I know it's an acid is because on the other side of this equation, it's missing its hydrogen. In Bronsted-Lowry, if you give up your hydrogen, your hydrogen, the other word for hydrogen is a proton. If you're the person who gives up your proton, you are the acid. Okay. So who are the people who are giving up? HSO4 is giving up. I am going to just erase this because when you're looking at an equilibrium reaction, as people move through the equation, their positions change. In other words, a person who gave up on this side, who's an acid on this side, on the other side, they now have room to pick up a hydrogen. So they actually become a base on the other side because they could accept a hydrogen. Okay? If you were the person who accepted the hydrogen on this side, you took the hydrogen and became H3O, you're actually the base on this side. But if you look at what happened to him on the other side, he now has that extra hydrogen and he could give it up, which makes him an acid over here. Now that we have some fancy lingo for that, over on this side, on the reactant side or the right side of the equation, we just call them the acid and the base. On the other side, when they've switched teams because of what happened to them, right now I've picked up a hydrogen, so I could give you a hydrogen. I have an extra one. I become the conjugate acid. But from what I can tell, they've stopped using this language on the Regents to like not confuse you as much. But just so you know, the people who are on the reactant side who have switched teams, basically, they become the conjugate acid and base. Okay, so if you are an H plus acceptor here, you're talking about somebody on the reactant side and somebody on the product side because this is a reversible reaction. It goes in both directions. So I can be that over here, but over here I could be the opposite, right? So who is going to take? Those are my bases. So I'm looking at water and SO4. So now I just have to find them. And here they are, choice 2. Okay, so there's a lot of decoding that has to go into these multiple choice questions. That usually is the number one issue my students have, which is they think that because it's a multiple choice question, it should take them 3 seconds. It's not going to take you 3 seconds. There's a lot of stuff you have to break down here. If you want to do those questions first that are easy and quick for you, sure, just watch out because they've put little traps in every question. But also don't overthink it to the point where you get it wrong. All right, so I think for the next topic in the next video, I think I'm going to do all of aqueous reactions. All right, so again, I'm going to link all of these slideshows in the description. There are 3 of them: heat equations and potential energy diagrams, equilibrium review, so there's practice questions in there, and a whole review of physical and chemical equilibria. So it's a little worth it for this because it can be a big chunk of questions. If I'm not mistaken, I was very disheartened to see on other Regents, sometimes it's really a lot of questions. I mean, it was 8 points on August of 2024. It was 10 points on January 2025. And this past June, it was 9 points. So it's pretty steady between 8 and 10 points. And since there might be part twos, like here, there's part twos for you to practice. It's worth it for you to pull the slideshows up and make sure you have the core curriculum out so you could tell what exactly are you supposed to be looking for as the right answer. All right, that's the end of energy and kinetics. Sorry it was so long, but I will index the video so you can jump around. See you next time.